This is Thiagarajan. So let's see something about the grade compensation of curves in Indian railways in this video. Okay, so what is the grade compensation on curves? So before that, we must know about the ruling gradient. What is ruling gradient? The section. As you all know, if you take a particular section X and Y, always, the vertical profile will not be flat. So there will be rising gradient, there will be falling gradient too, okay. So while we are constructing our formation, we will, we have to consider various aspects, and should be optimized to cost of constructions, okay. So that is why, we will follow the existing, the topography of the section between X and Y. At the same time, our gradient, whatever we are providing, our rising or falling gradient should not be much steeper also, okay. So as far as possible, we should try to provide a flatter gradient. Because you all know, when normally, vehicle when it's climbing over the gradient will be little tough because it has to put some extra effort, tractive effort. So that sometimes it will decide your hauling capacity of the train. That means the loco power and maximum load, how much it can carry. So all those things, will be decided sometime based on the gradient available in this section. Okay, it is one of the factors. So here, the ruling gradient is what? The ruling gradient is the steepest gradient on a particular section. If you take a particular section, the steepest gradient will be your ruling gradient. Because that will decide, okay, that will be the deciding gradient. So for which, the entire thing will be designed. Your loco power and maximum load carrying capacity of the goods train, everything will be decided. Okay. So if you take our Indian railways, and we have complete the network of railway track, and entire this is classified into so many routes. We used to say some group A route, group B routes, group C, and D and all based on the speed, maximum cycle speed of the train. It will be classified. Even the routes also classified internally, okay, in sections. Sometime, we used to say some Madurai to Tiruchirappalli, Tiruchirappalli to Viluppuram, Viluppuram to Madras, Viluppuram to some, okay, Vellore. Like that, sections will be divided into so many sections. Suppose if you take your Tiruchirappalli to here, Viluppuram section, this will be one station section. There, the all details will be available for the particular section. That means what is the maximum cycle speed of the train here. Okay, the passenger trains, how much speed it can run, and what should be the goods train speed. So what will be the maximum load the particular section can carry goods train, and what is the speed has to follow. Okay, driver has to follow while negotiating the turnout, and what all the grades available, what all the speed restrictions, permit speed restrictions available, and like that, the gradient also will be available here, the details. And here also the ruling gradient, that means the steepest gradient what is available in the section also will be available here in the section. Okay, for the guidance of the loco pilot, everything will be there. Okay. Here, as I told you, the particular section, the ruling gradient will be fixed. So, suppose, for example, here, Tiruchirappalli to Viluppuram, maybe some 1 in 200 ruling gradient will be there, max steepest gradient available. Like that, if you take your Viluppuram to Vellore, here, sometime, like hill area will be there. So here the gradient will be somewhat steeper. Here, maybe 1 in 100. So when trains, the loads are decided, here it will be decided for the 1 in 200. But whereas here, Viluppuram to Vellore, it is for the ruling gradient of 1 in 100. So sometime, the ruling gradient will be the deciding factor for fixing the hauling power of the train, and also what type of power has to, attach with the goods train, and what should be the maximum carrying load capacity. Everything will be fixed based on the ruling gradient of the section. Okay. So many resistance will be there considering those things. It is one of the factors. It is a major a factor as far as our tractive resistance are concerned. Okay. So when this is the case, sometime what will happen, the ruling gradient may combine with a curve. Okay. Because the ruling gradient will provide some resistance, and for that everything will be designed. But unfortunately, in some situation arise, the ruling gradient will combine with the curve. Because when it is joining with the curve also will provide some additional resistance. Curve resistance will take place. Okay, apart from this resistance due to the gradient, the curve resistance also will add together, and sometime the total resistance will exceed in the limit. So in this case, what we are doing, we are in the compulsion to do some compensation. Okay. So in this case, what we are doing, if that is the case, what we are doing, we want to keep the resistance within the limit. For that, what we are doing, we are slightly flattening the gradient, ruling gradient. Okay. So that the total resistance because of the gradient and the curvature should not exceed the maximum limit of the ruling gradient. Okay, resistance. Okay, so that is called grade compensation. Okay, so when ruling gradient falls on a curve, and how much reduction we have to give. Okay, how much flatness we have to ensure. So that we are going to decide. Okay, that we are going to discuss here. And for that, Indian Permit Manual has provided some stipulations that we are supposed to follow that. Okay, that we'll see in the coming slides. So factors causing track resistance. You normally it is the resistance because of the degree or radius of curvature. Sharper curvature will give more resistance. Okay, and train load. Okay, and curve resistance is higher at heavy loads. Okay, that's also there. And gradient. Okay, more the steepness of the gradient, more will be the resistance. So these are all the factors. Okay, increasing the track resistances. Okay. Further, let's see now something about the effect of the gradient as well as the curvature. So already I have put on one video. There I explained about the various tractive resistances. Okay. So there also I discussed about this the resistance due to gradient and the curvature. Okay. But here, as far as the subject is concerned, the curve compensation, the two resistance are important. That is resistance due to gradient as well as the curvature. Let's see something about it. Okay. So in what way the gradient affects and also the curvature. Okay. If you take our gradient track here, this will be our theta. That is based on your gradient. This angle of inclination. For example, this if we take a 1 in 200 gradient means what? For 200 unit, one unit vertical rise is there. Okay, that used to say 1 in 200 gradient, and for that the inclination will be equal to theta. Tan theta equal to 1 by 200 here. So opposite by adjacent side. Okay, tan theta equal to opposite by adjacent here. Okay, here our vehicle is running on a gradient track. Here this will be your train, and load will be acting vertically, W, and this will be the line normal to the gradient track. Okay, the resistance will be equal to along the gradient line. So let us take this triangle. This triangle will be a similar triangle because this angle of inclination is equal to this angle, because both lines are normal to the corresponding the lines of the gradient. That means this line normal to this one, and this line normal to this gradient track. So automatically the angle of inclination is equal to this inclination. So both are similar triangle now. So we want to know about the resistance to gradient. Let us take here sin theta. Sin theta means what? It is opposite side by hypotenuse. So sin theta equal to RG. Here it is our resistance due to gradient. Let us take this acting along the gradient. Okay. So sin theta equal to RG divided by W hypotenuse. But for approximation, the tan theta equal to sin theta, because of the gradient, very very meager. So 1 in 200 means, if we take an angle very very negligible, meager. That is why, so approximately we take the sin theta equal to tan theta. Okay, so tan theta equal to here RG divided by W, whereas tan theta equal to our gradient. Okay, it is equal to our gradient. So here, if you want to know our RG equal to W into tan theta, where tan theta equal to our gradient. This will be your expression to find out the your resistance to the gradient. Okay. So here it is directly proportional to the load. More the load, more will be resistance. At the same time, more the inclination, more will be the resistance. Okay, steeper gradient will have the more resistance. For example, here suppose we have only 200 gradient, 0.5%. That means and load of 20 tons, how much? So substituting here 20 into 1000, convert into kg into gradient 1 by 200, 100 kg. For 20 tons, 100 kg loss resistance will be there. That is for 1 ton, it is 5 kg. So this will be the your expression. This will be the amount of resistance. Okay, because of the gradient effect. Okay. So similarly for the curvature, if you take let us take a curve on 2 points. Okay, here A and B. We take this portion of track in the curvature. So inner rail length is lesser than the outer rail. So outer rail length is longer than the inner rail. So when the train is negotiating the curve, so this outer wheel has to cover a longer distance than the inner rail here. So because of that, there will be some resisted movement will be there. So though we are providing some coning of wheel, everything is there. In spite of that, there will be resisted movement because of the difference in length to be covered by the wheels, that is the inner and outer wheels. Okay. So because our because our wheel it's a fixed base. Always our outer wheel will have the angle of attack rubbing against the outer wheel and take the turn. So thereby there will be a resistance, always sliding friction will involve, and there will be some resistance because there is the resistance is based on your curvature, okay, as well as your gauge. Okay. So let us take here 2 points. The length of inner rail. Suppose let us take a distance along the central line of the track. The D equal to R into angle subtender. Arc length equal to arc length. That is D equal to the radius into angle subtended center. So between the 2 points. Okay. So this is, suppose when you take your inner rail length, it is R minus J by 2 alpha equal to your distance, okay, to be covered by the train by the inner wheel. Like that, outer length will be equal to R plus J by 2 into alpha. So here, more the gauge, the more will be the difference. More the gauge, more will be the difference in the length to be traveled. Okay, length to be traveled by inner wheel, by outer wheel than the inner wheel. Okay. And also the alpha is based on your curvature. More the sharpness of the radius, more will be the inclination angle, this angle subtended center. We take 2 points, same, suppose 100 meters if we take for a curve of some sharper curve, that will be, okay, that will be more the angle than your this one, okay. Longer radius is a curvature. Okay, so using this concept, the resistance due to curvature has been expressed in the form of equation RC equal to FG divided by R with some constant. Okay, where F is equal to sliding friction and G is equal to trackage and R is equal to radius of the curvature. Here, because of the rubbing action, continuous contact, the sliding friction you are considering here, and here the G is since it is in a numerator, the resistance will be equal to direct proportional to the gauge. More the gauge, more will be the resistance. At the same time, Since R is inversely proportional, okay, more the radius and lesser will be the resistance. Okay, sharper curvature we have more resistance. Okay, and the constant, of course, because load also will contribute something for resistance because of the, you know, some constant has been added here, multiplied here. Okay, so based on this concept and based on the trial and this in Indian Railway, okay, so this has been made, that is the resistance due to curvature for PG equal to 0.004 W into D degree of the curve. Okay, that means 0.0004 W D for broad gauge, and meter gauge it is 0.0003 WD, for narrow gauge it is 0.002 WD. Okay, using the relation, so are able to get the amount of resistance to curvature. Okay, and for example, you see for 2D curve for load of 20 tons, how much is coming? Point for BG, if you take 0.004 into D, it is 2 degree curve, and load we take 20 tons in kg, 20,000 equal to 16 kg it comes around, and for 1 ton it comes around 0.8 kg. I think this is the amount of resistance due to the curvature. It is based on your sharpness of the curvature. Okay, of course in BG, suppose BG only everywhere is, and BG will be the constant, when G will be the constant, and based on your you know, radius of curvature, this the amount of resistance will vary. So sharper curve you have the more resistance, okay, than the flatter curve. This is due to the effect of the gradient and the curvature. Okay, so the way grade compensation shall, you know, already we have discussed, you know, the avoid resistance beyond the allowable limits and ensure train maintain their hauling power. Okay, so that, you know, once it is fixed for some loading gradient, sometime, you know, if the gradient falls in a curve, it then there is an increased resistance will happen. Sometime the way the, you know, loco not be able to haul the load, and sometimes there will be loco failure, and we have to send some you know, helping locomotive. Okay, and reduce the tracting effort. Okay, lower the additional effort for locomotives. Okay, if the gradient is normally flatter, always, you know, it will reduce the additional effort for locomotives, and ensure safe train operation on curves. And if there is any struggled moment is there because of the curvature, because of the gradient, there will be, you know, there will be skidding, slippage will be there. Okay, sometimes there because of the impact, the rail may, okay, fracture, and loco may fail, and all the problem will take place. That is why, so we have to keep the resistance within the limit and for the design load. Okay, now let's see for the grade compensation what IRPWM says. So as per IRPWM para 416 compensation for curvature, it provides a standard formula for grade compensation. Okay, it's based on your radius of the curvature. So already we have discussed about the effect of gradient as well as the curvature, in what way it affects and how much resistance it will offer. Okay, more the steepness, more will be the resistance. At the same time, sharper the curvature, more will be the this one, curve resistance. So based on that, this standard formula has been given by the Indian Railway Manual for grade compensation. 70 by R% or 0.04% per degree of the curvature. So this straight away you can follow that. Okay, so here you can see the R is in denominator. That means it is inversely proportional to the radius. So sharper curvature, you have to provide the more compensation. Okay, and vice versa. So this formula we can straight away follow that. Where R is the radius of curvature in meters, this formula ensures the precise adjustment. So this is as per the Indian Railway Manual, para 416. This we are supposed to follow that. Okay. For example, here the rolling gradient is 0.5, that is 1 in 200 particular section. The radius of curvature is 583 meters. And compensation we are supposed to give how much? 70 by R. It is for BG. Okay. 70 by 583 equal to 0.12%. We have to give the compensation. Okay. So that percentage you have to give compensation. That means compensation grade how much? Already in the 1 into 1 means 0.5%. So minus 0.112 equal to 0.38. We're converting into gradient, 1 in 2 to come. Instead of 1 in 200, and we have to ensure gradient of 1 in 264 along with the curvature of 583 meters radius. Okay. So this is something about the example, and this way we are able to ensure while we are doing the construction of the formation, when rolling gradient falls with the curvature, we are supposed to ensure the gradient like this. Okay. Okay, when this is a gradient 1 in 264, along with the curvature, what will happen when train negotiates, and it will face the resistance equal to 1 in 200 gradient, what it is in a normal case without curvature. Okay, that means that's what it says. So let's summarize what we understood. The grade compensation minimize the total resistance on course, ensures efficient operation. Okay, so whenever the rolling gradient joins with the curvature, and we should try to flatten the gradient so that the total resistance should not exceed the limit. Okay, so safety point of view also it takes care. Okay, so this will conclude this video. Let's see in the next video. Thank you.